let's start this. I would like to a little bit talk today about PQC and then go over a little bit what's happening with the standardization and the challenges of actually implementing PQC real-world applications. So, okay, very good. So NIST announced the PQC algorithms. I'm sure people, folks in the room already have familiar what's going on with PQC standardization, but this happened almost a decade. It took since 2015 at a PQ Crypto conference in Japan. NSA said we need to act now, actually almost a decade. And then NIST started bringing up algorithms that we would like to study. People submitted 86 algorithms over there. And then finally, by 2023, these algorithms got chosen. Crystal Kyber or FIPS 203, ML-DSA, the Lithium, Falcon, and the Sphinx. Very recently, also Falcon numbers are coming up. Sphinx also another hash-based signature from round 4. I think you know that HQC recently got introduced as a winner, and documentation is coming up for that too. HQC, ML-KEM, and among these, NSA chose only ML-KEM, Kyber, and ML-DSA as a mainstream for PQC standard. I think standardization for national security algorithms. So we have also on-ramp digital signature algorithms. The reason is algorithms that we have is kind of uncharted territory we are facing here. Some algorithms, they're offering very smaller key size, signature size, but storage-wise, they're not efficient in terms of the communication bandwidth problems. We would like to have digital signatures that are as much as possible small in terms of public key and signature size. But what we have here, for example, the Lithium, Falcon, Sphinx. Sphinx is very huge. I think, you know, it doesn't work, even fly into some applications that we would like to have, like real-time kind of time-sensitive network kind of applications. So that thing is also ongoing. There are 10 algorithms there. I think we've been supporting these algorithms since the beginning of 2016, I think, and many others too. So on the side also, NSA is looking into for CNSA, commercial national security algorithms. These algorithms are the ones that DoD kind of applications folks are supposed to use. For example, only Kyber, Lithium, no matter what's going to happen to Falcon, Sphinx, or HQC and others. But NSA, I think they made the decision to go with only these algorithms. Okay. And the XMSS LMS, you know, XMSS LMS for as Sphinx is stateless hash-based digital signature. XMSS LMS, they're basically stateful. You need to take care of the state for when you sign something. You need to make sure that your key, you're not using it again. And of course, AES 256, SHA-2 SHA-2 mainly for mainstream application. If you're using as a standalone hash function, you use SHA-2. And if you're using calling as a function, also recently NSA actually allowing using SHA-2 also for SHA-3 for kind of applications that you can get root of trust kind of applications. Okay. So there are, I think, more. Oops, it goes this way. Very good. So PQC agility is I think, nice topic these days. People are talking about that. At NIST had recently an event called PQC agility. A lot of discussions ongoing, happening in conferences. You go talk people, software implementations, hardware implementations, especially for hardware. I was actually yesterday at UK-US Semiconductor Security, Hardware Security event over there. Again, it came out, the US, I think one of the executive orders is actually about this topic, cybersecurity post-quantum, how you do it, hardware software code designed to address the agility, patches, updates, upgrades, over-the-air updates for if you're implementing in hardware and why hardware is important. So these are the terms that people are agree on these implementations, compliance with standard bodies, NIST, ETSI, ISO, Europe, China, a lot of standardization activities happening, also security strength. So for example, my iPhone or yours is using second level security, for example, level 3 of ML-KEM currently for messaging. Chrome is using same thing. Some applications, NSA only recommending level 5 security. So sometimes you don't need to level 135 or 235 for ML-DSA. Just security level. So how you handle those migration, retirement, how you want to turn off ECC, go to PQC after implementing these in hybrid or composite mode. And also composability platform and other things. These are all great topics, I think people focusing here. But after PQC got standardized, I think we see a lot of fast followers, first movers, for example, financial, FSI, SAC, telecommunications, aerospace, defense, all active transportation, even also medical devices for applications that FDA finally approved the cybersecurity, and crypto as an engine of addressing the cybersecurity should be there, and it should be also PQC. So a lot of activities happening here in terms of the manufacturing and chips. I think soon you'll see that your phone is doing PQC, and already some others are using based on the QRNG or quantum random number generators and other things that are quantum safe. So AWS, NVIDIA, HP, I think Zoom is already became PQC. CAVP is available for various algorithms, ML-KEM, DSA. SHA-2-3 already, they were there. And also, for no matter what CAVP you're doing for software or hardware, they're already available. NIST test labs, you can work with them. Google, you know that OpenSSL and many others, I think they're addressing this need, and that's happening very quick. So when it goes to implementation of software or hardware software co-design, that's the challenging thing that's starting from when we look at C implementations that NIST recommended we have to implement PQC. Well, actually as a reference implementation, but when it goes to actual device or implementation into products, that's different story. So that thing that our reference implementation is already implemented in ANSI. So if you would like to optimize them in for device level, you need to perform implement them in assembly, hand optimized assembly, or generated, AI generated, some kind of things. And also C to Rust. Rust is a new, I think, a memory safe language. It's not a new, I think it's pretty, maybe a decade, but still working here is becoming more challenging with C because C is not safe against memory. And you know that there is a program called Tractor Transfer All C to Rust, which is already happening. People that they would like to migrate from classical crypto to PQC, they are more than welcome to address the C problem here and just go to Rust. So also formal verification of C is already happening, and if you do Rust, then formal verification and other things are going to happen there, and also side channel protection. There are a lot of challenges actually here we see on side channel protection when you're implementing PQC in software, actually in C, and as well they're going to happen also when you're doing Rust. So I'll have it a little bit of that. Hardware implementation, same thing, FPGA implementation, ASIC implementation, side channel protection, verification and assurance. A lot of companies are actually ignoring doing formal verification for crypto when it goes to hardware implementation because it's really hard. It takes a lot of time, a lot of energy, and also you need to have right talent here as well. And hardware software co-design is actually here to help with the fact that we need to make things as upgradable, updatable, and agile. That was the discussion. How much you want to put in your hardware in silicon and how much you can put in your RISC-V or MCU over there to take control of the computational things for helping making things more agile. So hardware, software, I'm sure if you're in academia, you're already familiar with these, what's happening with hardware implementation. If you want to have dedicated hardware, very fast implementations, and also protection against real side channels, real protections, actually, I would call it sometimes, because software is not going to happen. Open source code, open source hardware, I think sometimes is not really available. There are some open source that are not well maintained. And also libraries, of course, higher agility is what software is possible because software is by nature is easy. So I think this is slide, everybody's talking about this kind of slides. I think no, not everyone does good cryptography, because sometimes we see that implementations are the problem, main concern of secure implementations, or actually good implementations, not with vulnerabilities. And that's the case of all these attacks that MITRE they put together over CVE. I think libraries up there, they're available on the database. You can take a look. And a lot of them, I think you can look at, for example, side channel attacks and even bad random number generators and many other things. So crypto engineering is actually, since I'm a professor as well, I teach crypto engineering course. We focus classical crypto. We start from finite field. I had a student currently working for NSA, they were mentioning, hey, when we go there, we just start for a year, we just study finite fields. So same thing in academia, we teach finite field arithmetic, computational things, from basic operations, computational things, and then we go build the protocols and implement them securely, and then try to attack them or make them side channel protected and many other things. So what happens with industry? Industry, basically, some companies, I think we put them like almost 30% for each, but some companies say, I can do that. I mean, I'm going to do myself. Some companies say, do it for me, or give me some start point to look at, see what we could do if there are right talent or right, I think, right timing. People would like to have their own, because licensing model, purchasing from others overseas, export control things are also becoming sometimes very challenging. So I have here a little bit of migration stages of PQC. So starting from performing risk assessment, I think in the past decade, people already starting looking into different algorithms. I think no longer you need to, as I think, implementer or integrator engineer into products, you don't need to be worried about the security of, for example, Kyber. Although there are folks trying to attack it, that's happening actually for RSA currently too, or even ECC. And attacks are getting stronger. Also, attackers are getting stronger too. And also, that's why we have various security levels to address that need. And then exploring PQC algorithms, which algorithm, as you saw over there, we have ML-KEM, DSA, Sphinx, and FNDSA or Falcon, and then many others are on the road of, in the next 5 years, we'll see them. And studying how to implement them actually into software or hardware, because software implementations are already, we've seen that they're prone to a lot of side channel attacks or even fault injection attacks, and then how to implement them securely in physically either hardware or software that's bring up side channel protection, timing, EM, and many other, I think, fault injection attacks and others. So FIPS 140-3, I think if you're familiar with it, level 3 and up, it's recommending highly performed side channel protection, non-invasive side channel protection. It should be there. So, and also is based on the ISO. I think standardization explains it very well, but FIPS 140-3 is just a kind of a cover-up on top of that. And then focus on deployment target applications, what you want to do with integrating securely in real-world apps or devices that you'd like to consider using them, and studying the reliable and high assurance implementations. I think formal methods, formal verification, it's becoming actually very important these days. You know, software PQC, formally verified, formally, not functionally. For example, sometimes you see ML-KEM, ML native, ML-DSA native. They're not formally verified. Actually, they're implemented, but they have been tested with those tools, CBC or even others for whole light, for example, for basically functionally verifying it. They're not very functionally, actually, mathematically, there are no proofs there. So formal verification, I speed up a little bit my talk here. So, you know, this is the basic of finite field arithmetic that we perform ECC over field of P to the power of 55 minus 19, or we call it 255-19. If you open your Google Chrome, you'll see that whatever ECC working with your ML-KEM is actually curved to 55-19. So if you want to just simply check this multiplier, of course it's a multiplication and reduction because it's a pseudo Mersenne prime. how many inputs we have? To the power of 55 times to the power of 255 inputs there, and checking it exhaustively, testing is not going to happen, maybe in our lifetime or even in the future. So formal verification is here to help us. So how there are no bugs or vulnerabilities here, and how we can prove it mathematically. And that's I think important thing here that people would like to ensuring the correctness of PQC algorithms. I mean, starting from the bottom, your finite field operations, arithmetic like multiplication, addition, inversion, squaring, and a little bit higher level like group level operations, and then protocol level, all they need to be verified, efficient. Key areas of PQC, for example, verification that people would like to address: mathematical proof, verification, for example, theorem proving, and then protocol level, software execution analysis, and ensuring that compiler security is working. Because sometimes you write your code in C, you get assembly, it generates you some assembly, right? You execute, good. Sometimes you'd like to add side channel or protection, extra things in your code to make it more robust and secure. So compiler is not giving you actually the whatever you put in C for side channel protection. You need to have it in assembly, hand optimized, handcrafted, and then add side channel there. You know how long it takes? If it takes, for example, writing a C code for something, some algorithm, a month, and if you'd like to have a proper, efficient masking, shuffling, protected, side channel protected, I think, implementation there, maybe it's going to take several months, for example, up to 6 or about a year, if you have right talent. So that's, I think, one of the things that people would like to see, what using LLMs or Gen AIs to help you address the gap from C, high-level languages, to low-level, machine level, to make things working properly for you, and actually implementing what it's supposed to implement. So there are, I'm sure you're familiar, Formosa, folks are working on, we collaborate with them, EasyCrypt, Jasmine. If you're writing some programming language and compiler in C or even low level, you can use Jasmine, and also Hololight and LibJade. For some, I think if you look at them, there is no actually one single tool helping you. Even look at Hack Conference. I've been high assurance crypto conference. It happens actually usually at the same time of real world crypto. There is no single tool, or even one or two. There are like almost 30 tools over there they listed. They're looking into verification. Something can do assembly, not CC, not assembly, or even not low-level computation, very high level. No side channel. Actually, now there is no, I even don't want to say complete, but 50% working tool for formal verification with side channel in place. So that's I think even AI is not that much helpful here. I think if people would like to study, address that thing as a PhD students or research work, academia, I think a great topic to look at it. EasyCrypt, I think we looked at it a little bit of working on PQC algorithm, for example, Kyber, you know, ML-KEM, looking into see how it could show you the encapsulation mechanism and decapsulation on the other side, the encryption, because sometimes errors over there giving access to fault injection attacks. One of the or side channel attacks, you know, one of the I think work that recently focusing on side channel implementations of software is not proper, because always you have some bugs and problems. Proper implementations of decapsulation, which is always prone to, you know, secrets are involved over there, and you can make statistically your secret independent from your other things, computational things. That's why I think studying here is a key thing for looking into that. So bottom line is, if I have an example here for ML-KEM, I think operation for the decapsulation. So if the adversary chooses two shared messages, M0 and M1, for example, A random one, for example, B is encapsulated and ciphertext given to the adversary. The attacker can query the decapsulation. You know, decapsulation is the one that, I think if you look at the side channel, first order, second order, third order, fifth order, all gets broken. Side channel protection of software, actually on embedded device, for example, ARM Cortex-M4, it gets broken. Why? Because you're running it sequentially. Always you may have not implemented properly things and it gets broken. And that's why people are always looking into how we can migrate from software to hardware, because I don't see any actually correct or proper answer for that. I mean high-level devices, for example, phones or laptops. You know that the side channel attacks on those devices are very complex, I would say. Even I have seen a lot of proposals from ERC people trying to study and understand if they can use, for example, genetic algorithms or genomic data or Gen AIs, LLMs, and other things to do that. Still unsuccessful. So I have not seen any side channel attacks on CPU level devices, or even, for example, high level ARM Cortex-A or Raspberry Pi 4, 5, whatever. ARM Cortex-M4, M0, M3, M7, they're very prone. And that's why, so back to this example. So if the adversary guesses B correctly without with a probability of more than 50%, then Kyber, we call it insecure, and you need to always prove like a kind of that works properly. Why Rust? So people are looking, studying memory safety. Memory safety is one of the crazy, I think, things that is causing a lot of problems. I think if you've seen that memory problem and vulnerabilities over there, I think last time happened in the flights got all delayed, canceled. A lot of the shutdown happened last year, I think. And C is never going to give you actually the opportunity to have it memory safe implementation. Sometimes, if you don't access, of course, good. If you access your memory, then so. And for crypto, always you need for, especially for PQC algorithms. And then defining semantics, mandatory initialization, built-in runtime check, secrets, and public. You look at these, all of them. These are not actually offered by C, except the high-performance thing that actually we have been able to address this one as well through Rust. The general understanding is that C is always faster in smaller, tiny devices, and also when you go to high-performance cloud-level implementations or server kind of applications. But we have been able to show that because Rust is also getting, I think, better and better. And that problem has been addressed, for example, for primitive implementations, for multiplications, SHA-2-3 implementations, and protocol level, I think it's getting already there. And we'll see more usage of Rust. As you know, I mentioned that the transfer to C is happening. So there are some tools that you can use. I think NSA developed, there is a company called Galva. I think they were looking into some code you write in, actually C2Rust is a program.com developed by Galva and NSA. I think it's available online public. You can write some Kyber code, simple code here, as you could see. And then you can ask to generate you the Rust. So whatever you write here, do you think that's going to be the translation or conversion transfer is secure, efficiently implemented? Actually, the address is no. And then you need some, I think, better tools. That's actually was to show only C2Rust is working. It's only working. It's not something that you can rely on it. You need to have your own development or use or tools that are working there. They need to be updated, upgraded, and a lot of research work is still happening there. So it's kind of a less safe, less readable, as you could see over there. I think to me it's not readable. I think maybe you. But sometimes folks can, you know that sometimes we provide binary codes to customers and then they come up with the actual code. So that means how attackers stronger could become. Okay. I went too much back. Okay. Okay, here. So pure hand written, but hand optimized implemented actually Rust actually is we call idiomatic Rust implementations. You know what's happening here? You can do all bound checks explicitly handling the like overflow, which is the key, I think, sometimes happening. I think there was a paper last year, I think people are studying at the secure implementation of ECDSA in most cases, and that overflow is most of the time is becoming, I think, challenging. Rust native type safety, memory safety, thread safety are there. No null pointer. That's why we highly recommend. And also you can have your side channel protection here written in actually already in Rust instead of I think waiting for. Is that here? Okay, suddenly it's going to go on the next one. I hope these are, these are final notes. So for PQC implementations, I think it's important to have security guarantees. Digital security, I think you need to have a lot of testing. You know, for VLSI design, when we design something, we do a lot of testing, even several times or sometimes more than the design itself. Formal verification is not an academic concept. That's why people are not looking into that a lot in terms of the testing and verification. But formal verification itself is a concept. I think it's not functional verification that sometimes people look into that. That's important. One of the examples actually is the last operation of elliptic curve cryptography, for example, or even RSA, when you use Montgomery multiplication or reduction. I hope you guys are familiar with that. There is a simple subtraction at the bottom. When your resulting thing is more than P, you just simply do a subtraction. Without that, you feed your device, it's working. Problem may not appear, but if you do formal verification, you can find it. That thing is actually brilliant. Tools like, I think Jasmine, EasyCrypt, I think are advancing. I think more work, I think is highly recommended on this domain. And also, AI-driven automation is the other thing I have. I think we're following. There are a lot of activities happening using LLMs. LLMs, they have their own, I think, shortages and weaknesses helping with the efficient and proper implementations. With that, I would like to stop here, and then I take if there are any questions. Thank you very much, everybody.
Thank you. Related to memory safety, you're grouping C and C++ together. As you may know, like the C++ committee is not so happy about this. They're saying, well, if you're using a subset of the language, it is possible to go for C.
Yes.
What are your thoughts?
Not merging, of course. That's separately C to Rust or C++. So that's what.
Because then you could say maybe Rust is not safe. You need to do safe Rust. Right?
Yeah.
It's a subset of the language.
Sure.
Yeah.
Subset of language, of course, yeah. Very good.
Thanks, Nikki. More questions for Reza? A little slow after lunch. I'll throw one out there, Reza. So I loved your slide on the translation from the tool you were talking about, like from C to Rust. I think you had the Kyber/ vulnerability on the actual slide, right? And so
yes, yeah, that's
okay. So, but it's a little bit cheating in the sense that when you put up the Rust, you had already put the countermeasure to Kyber/. So I guess your point was that insecure C maps to insecure Rust. So what would your take on side channel resistance in Rust? So side channel vulnerable Rust still leads to vulnerabilities, right? So what would your comment be there on how Rust can help on that front?
Yeah. So what we studied actually is if you write your C, you convert to Rust. If your C is robust, your converted Rust is not robust. Whatever robust means, side channel protected or efficiently implemented or even a constant time implementation of C doesn't go to Rust. So that's what we need help here. We need help of LLMs or other things to help to make that, I think, transfer or translation as point-to-point as possible. So second thing, if we have a vulnerability in C implementations, that goes actually to vulnerable Rust as well. So if I have a vulnerable C without, for example, some problems there, non-robust C translates to non-robust also Rust as well. So again, we need help here to understand that if there are problems with C, you're not converting actually exactly everything there. So we need some AI to help here as well. That's, I think, the next thing. And third one is actually if you're implementing your C side channel protected or robust implementations, okay, Rust is not, it's supposed to be, but whatever we currently have, it's not giving you the correct implementations of side channel protected C into Rust. So that's these are the three scenarios. I think I can talk about more scenarios here too, but that we studied. So, but if you write it in actually Rust from the scratch, I don't think people would like to do that, because in the next 10 years, we would like to, I mean, not me, but US government defense would like to get rid of whole C in the next 10 years. And that's started from a DARPA program called Reactor, and that's going to hopefully happen. But if you're just converting from C to Rust, a lot of vulnerabilities will show up. Solution, writing from the scratch, then there you go. That's, again, another, I think, its own problems. But very good question. I hope it answered.
Yeah, no, great
somehow.
answer. Great answer.
Yep.
Thank you, Reza.
Thank you. Thank
Got a
you.
question from Jake here. I'll pass the mic.
So in looking at the, going to C, going to Rust, isn't it true, though, that in order to optimize, you still end up implementing an assembly under the hood?
Sure.
And so how does the DARPA project propose to get rid of?
So, so at this point, DARPA is looking into general C to Rust. It's a project started with that. There is another program called the Resilient Software Development with Formal Verification and looking into Rust. That's more in depth. People would like to apply into a crypto system, actually, whatever they do over there. But efficient implementations of just C to Rust. Rust is becoming as, I mean, for crypto implementation. For others, maybe C is very high performance, which I am sure at some application. But for crypto implementations, you can make your Rust as fast as your C reference code. But what makes C faster is actually your hand optimized of operations on the bottom low level, right? Rust is capable of doing that. Yes and no. Some places yes, some places unfortunately no. So if you write very hand up, and the reason is actually what we have in whatever macro MCUs, but everything is based on the mentality of what's going to happen there, C, and then assembly instructions there. So RISC-V is helping a little bit. Hopefully in the future you add more instructions that ISA is there to address the need of maybe Rust there too, but it's an ongoing thing. So I have not seen hand-optimized assembly implementation Rust for crypto algorithms, or I haven't seen comparison over here. But the point is also portability is also important thing. Of course, it might be out of topic, but portability is also important here. That how much you want to go from devices to devices. You don't want to get configurations of various implementations, and because it ends up getting bigger and bigger if you have more. These PQC algorithms, how many PQC algorithms we have so far? 6, 7, right? For 3 security levels. And then if you want to have low stack, high stack, and then you'd like to have faster, smaller, medium, it's almost, if you multiply them, is more than 40 combination of algorithms that you'd like to maintain. And maintaining these are also challenging, especially with the fact of, for example, if you're integrating to TLS and other things, that would be. In the past, we had ECC. ECC, ECC was, for example, ECC prime curves, binary curves. Nobody touched binary curves at all, right? We got stuck with prime curves. And in the past 25 years, everybody used everybody. I mean, no industry adapted binary curves for applications. So that's, I think, similar thing would happen. We work with a smaller set of curves or algorithms. And then you focus making dedicated software implementations, or you do simply dedicated hardware implementations.